Hello, everyone. My name is Paul James and my colleague is Martin, and we're here to present our project crop Intelcast with having the keywords explained in detail. First of all, we all have to agree that coffee is one of Uganda's largely exported crops as per the statistics of 2023 to 2024. It brought millions of dollars into the country. And with further research that we went into, we found out that calculating the amount of coffee that is being got from a particular plantation or from a particular tree, people used to use extrapolation as being shown by the table below. And extrapolation lacks standardization and it was biased among others. So let's talk of our related works. Yeah. Uh, First of all, uh, the machine learning was introduced into agriculture by Subhadra Mishra alongside his colleagues, and they talked about attention mechanism and capsule networks, among other models. For which case, in our scenario, attention mechanism helps us focus on important image features, reducing noise and improving accuracy, while capsule, on the other hand, improves feature representation and preserves spatial relationship between objects, making them ideal for small object detections like coffee cherries. And contrastive, on the other hand, NSS distinction by distinguishing uh, difference in cherry ripeness. And knowledge distillation, we just simply use the larger model to train many smaller models. So our problem statement, we generated it from manual yield estimation, lacking standardization and leading to inconsistent yield predictions and poor resource allocation, uh, which was untrustworthy. And why this matters, farmers and policymakers struggle to make data-driven decisions due to uh, unreliable forecasts and inefficient resource allocation impacts profitability and sustainability. So when we go of computational problems, let's talk of contrastive learning computational problems. There's difficulty in learning highly discriminative and robust feature representations for different coffee yield classes, especially. Let us talk of under various lighting and background conditions. And why is this actually important? Contrastive learning forces the model to learn features that differentiate similar and dissimilar samples. Uh, well, that is making feature extractions stronger and generalized. So when we talk of attention mechanism computation problem, there's inefficient focus on critical image regions, that is actual copy shares versus the background leaves, leading to dilute model performance. And in this case, the attention allows the model to prioritize important features in images, improving both prediction accuracy and model inconsistency. Now, on the knowledge distillation, there's need for lightweight, let me say, highly performing models for deploying in low resources environments like mobile devices and or limited internet areas. And why is this important? Well, knowledge distillation transfers knowledge from a large or let me say accurate model. That is what we call usually a teacher model into a smaller model. And it is an efficient model, a student model without significantly losing the accuracy of it. Yeah, so when we go to the next page, let's talk about recite questions and objectives. So simply, when we develop this one here, there are some questions that we add to ask what our system would do. That is, for example, can contrastive attention knowledge distillation improve the accuracy of coffee yield prediction? And how does the performance of capsule networks compare to traditional CNN and SVMs? Now, what role does contrastive learning play in feature extraction for yield estimation? Another question is, how can knowledge distillation optimize model deployment without sacrificing accuracy? And how does multimodal data fusion impact the reliability of predictions? Uh, so research contribution is in this case, we develop uh, a capsule neural network plus attention model to automate the yield estimation process. And then we also developed a contrastive attention knowledge distillation combined with capsule networks frameworks for coffee yield estimation. We propose future integration of the system with IT sensors and drone captured multi-spectral image for real-time and large-scale coffee yield monitoring. This is the future plan for this project. We benchmark our purpose models against the baseline models and demonstrate superior performance. When we come to methodology and system architecture, our methodology different. Actually, it comes from data analysis, whereby we had to look for image quality assessment. We assess our images, then we went for data argumentation, and then we process our data set in this case. Then after doing all that, we went for feature extraction. That means we had to identify features within the main features within our images in the data set, of which we are talking of cherries, leaves, and canopy. Let's focus on the cherries for now. And after doing that, what did we do? We went for self-supervised learning components, which is the contrastive learning, then feature representation learning, and teacher model training. And the teacher model training always has a teacher model, and the teacher model, the knowledge from the teacher model is transferred to the student model, and then it gives us the well-simplified work, which is accurate, and that is what we call distillation process. Now, when we go to the system architecture, we had to train our model first. And how did we train our model? We first loaded the data, then we extracted the features that we wanted our model to focus on, then we started training the model and then evaluated. Now, when we tested the model, we loaded that data definitely from our data set, then we extracted those features and we predict using the model that was trained, and then we evaluated. So when we go to data description and exploratory data analysis, well, our data description, image specifications, as we can all see, 10 MB to 12 MBs. And then the dimension is 4,000 times 3,000 pixels, and resolution is 72 dpi, which is definitely not the perfect resolution, but yeah, this is a good resolution for now because we need to train our model to detect images of even lower resolutions. So we went and annotated using RoboFlow, and then we got the classes as unripe, ripening, ripe, and coffee trees. And then we annotated all the instances, giving us all the values that we are seeing there. So after that, we tested our our annotated data set, and it gave us the graph that is a distribution of images in each class, which is in train, valid, and testing, and it's showing us exactly what we wanted. And that was how it was from our RoboFlow. So we now tested to count the number of cherries, and that is what we could see there. When we continue, we had also to plot graphs showing density plot of canopy growth. And that one shows our canopy, and the next one is canopy coverage percentage in coffee plants, which is frequency against the green pixels. So we went ahead and did all these graphs in exploratory data analysis. So thank you.
Hello everyone, my name is Massimo Anguzi, and I'm going to be taking you through the rest of the results. These are some of the graphs. The top graphs are gotten from the attention-based model, and we are seeing the precision confidence curve, the F1 confidence curve, the precision recall, and the recall confidence. These curves enable us to tell that the model was able to train, and after training, it was able to determine that this, from the F1 confidence curve, we're able to tell that it got to train, and then after determining the right confusion matrix from the CNN with the hyperparameter of the KNN. And here we are seeing that over 69 images were able to be detected as the canopy density. and the rest were determined as follows. And then we have the PCA, which is showing the different green cherries, yellow cherries, and the red cherries. And then we have more results from the support vector, the top graphs, and then the confusion matrices. As you can see from the confusion matrices of the SVM, that 47 were able to be detected as high. The 1 and the 0 are presenting high yield and the 0 presenting low yield. And we are seeing that 47 from the validation set was able to be predicted as low yield, yet it's actually low yield, and 10 of it was able to be predicted as low yield, yet actually it's supposed to be high yield. And then we have results from our CNN model. And then these are some of the tables that we obtained from the different models. The regression model, which was able to predict 5 kgs, and then the explainable AI results. This is from our best 2 models, which was the CNN attention model and the regression model. And you're seeing that it's from, we used 2 techniques. We use the lime, which is the pictures on the left hand side, and then we used the lime, which is on the left hand side, and then we use the bounding boxes to show the different areas that the models focused on. So as you can see, we have our worst 2 models where we have the lime and the salience map for the 2 models. So in the first top, we have the contrastive model, and then down we are having the images, and we can see that the CNN to model very well to show what it focused on, and the salience map for the contrastive model was also not clear. And then from our 10 models, this is the comparative performance, where we are seeing that the CNN is having the least error. We focused on accuracy, precision, and the mean average error. So the attention mechanism was able to focus on the features that we need. And then it outperformed all the other models, and it was easy to implement since it was light. It wasn't as heavy as the contrastive and the knowledge distillation that we wanted to use. And the capsule, on the other hand, was having high precision, but the accuracy wasn't according. So we deployed our model using Flask API, and with that we created UIs where the user is prompted to upload the image, and after uploading the image, as you can see, the user gets results of how many kgs they are able to get, and this is the flow of how the system works. So our project was created using the yellow V8 as the attention mechanism to be able to detect and classify these coffee cherries. And we also incorporated in a formula, which is shown, and each of the box was taken to be 2 kgs, so it's standardized. And then we have our trademark name, which is Crop Intelcast. Our model achieved high accuracy and better feature extraction and efficient deployment compared to all the traditional methods. But otherwise, we faced some limitations like the data inconsistency, computational resource limitation, limited data availability, model complexity, and environmental variation, which affected the quality of the images. Our future works involve us incorporating in IoT-based sensors to cater for all aspects that affect a plant to grow. And then from there, we plan to do regional training workshops for the agriculture farmers, and then incorporating drone imagery and expand our product to different crops. We'd like to thank Macquarie University and Unipod and Mendiflow and RoboFlow for enabling us to get the data sets, and then Uganda Coffee Development Authority and the National Coffee Research Institute for giving us more insights, and for Zenti and Chen, whose work we based on to create our project. Thank you.